Alrighty folks, welcome to our next video in the Tesla project. And as you can probably see here, we've been quite busy. I know in the last video I said that I would be doing a video where I had the inverter connected back up to the motor, and we were kind of gonna run it with the rat's nest logic board that I had set up and so forth. But I ended up having to go into hospital there this week for a few days, so that kind of screwed up that plan. But figuring that I'd be hours waiting, I brought my laptop along and managed to get quite a lot of the work done here on laying out our new logic board. So what I thought I'd do is we just do a little quick video here and just walk you guys through some of the circuitry, how it actually works just in the broad strokes. And so then we'll be set up pretty much hopefully soon to start ordering some PCBs and we can get a prototype made. So this package here that I use is called Design Spark PCB. It is probably not the best PCB design package out there, but back in the day one of the first packages that I used was called Igbt, and it was quite a steep learning curve for me at the time. But so Design Spark is based upon Igbt. So when I got back into doing this kind of stuff years ago, I just ended up falling into this particular package. It works well for me, and things that I like about it is that there are zero restrictions on this at all. So there's no board limits, pad counts, any of the kind of nonsense that you get on a lot of free packages. It outputs all the right kind of design files here. You can do your Gerbers and pick and place files and all that kind of thing. So I use this package both for professional and hobbyist purposes. So anyway, the one disadvantage of it is it only has a Windows version, so I have to keep a dual boot on my PC, primarily just to run this particular program. So anyway, enough about my computer habits. So I suppose above all the videos that I made out this particular project, this is probably the one that's going to get me the most people say, Damien, you're doing it wrong. So, okay guys, I might be, but this is the way I'm doing it. This is my design, so this is what you're gonna get. So, alright, let's jump straight in here and we will go into the heart of the beast, which is the STM32F103 microcontroller. It'd be the correct term to use. And this guy here does all of the motor control and all of the other functions that the inverter does, keeping in mind that this design is based upon the one done by Johannes Hubner. So we're just basically taking a lot of we're certainly taking all of the software that he has written, and we're taking a lot of the hardware design too, and we're basically modifying this to work with a surface mount PCB and adding in the bits and pieces necessary to run the Tesla inverter. So basically what you're looking at here now is the microcontroller itself, its JTAG programming port. We've also included here the single wire programming port, which we may need for future development. Basic things that you do on a microcontroller, they're the same the world over. You have reset circuits, power filtering, all that kind of thing. We have two crystals, 8 megahertz main crystal and a 8 megahertz and a 32 kilohertz crystal here for timing. So we have all of our I/O lines, putting a few LEDs on here, one just to give me a check that the 3.3 volt line is working, and one just to show that we have a heartbeat going on within the microprocessor. So jumping over here then to the connectors section, this is where we have all of our JST CPT connectors to basically where all of the things from the Tesla inverter plug into our logic board. So we'll see here, for example, this is Con1 is the DC bus sensing plug, which is an 8-way, and these are the various signals that we are connecting. So we've got temperature sensors, we have the external connector here that connects to the amp seal plug, where the external connections go into the drive unit. Now it's probably worth noting that we have some reassignments here, so certain signals are being replaced. So for example here, if we look at pin 20 here, that would be the high voltage interlock in from the normal Tesla situation, but we've basically changed that to be the forward input signal. So I'll be going through all of this in more detail when we have the prototype running, but just suffice it to know for now that we are reassigning some of the pins on the external connector. So moving down then, we have the IGBT driver connectors, the current sensors, more temperature sensors, and even more temperature sensors. Now, while we're on the subject of the temperature sensors, this version 1 board at the minute reads one heatsink temperature sensor and one motor temperature sensor. The Tesla drive unit has 7 NTC type temperature sensors on it. So we will be modifying this design so that we can read all of those sensors. But just to get us moving, I'm just going to read 2 of them for now and get things moving along, and then we can fine tune. Because the one thing you can be certain about with a design like this is you won't have the first PCB made, but you'll think of something else that that you want to modify. So current sensor scaling is very, very simple here. This basically uses a dual op amp to scale the 2 Tesla current sensors into a 3.3 volt range. Basically they work in that 2.5 volts represents 0 current flow, and then it swings from 0 to 5 volts to represent minus probably over 1,000 amps to plus 1,000 amps. So we basically use the little op amp circuit to rescale that so that it normally sits at half of 3.3 volts, so 1.6 something volts. So that's all that this particular part does here. It's not very exciting. CAN bus connectivity to the microcontroller. It's via the Texas Instruments SN65HVD234. Very straightforward here. We've just got the chip, the decoupler cap, and the termination resistors. RS232. Yeah, that's been something that's caused me some problems on this on previous designs with this inverter, in that the USB chips don't really like the idea of sitting around high noise environments when we're pumping hundreds of amps into a motor. So we're going old school here. We're going to use a standard RS-232 level converter chip here to give us traditional RS-232 lines coming out of the inverter. Now, what I would hope to be doing is that the RS-232 will be just used for programming and setting parameters initially, but then we'll be able to move the whole thing over to CAN bus. So that's there. Power supply, it's a pretty simple beast. We use a buck converter chip here to drop the 12 volts to a 5 volt line. Then there's a further low dropout regulator that generates a 3.3 volt line from the 5 volt. And then we have a little charge pump converter here to generate a minus 5 volt signal from the 5 volt line. There's only one part of the Tesla inverter that needs a minus 5 volt supply, and that is the voltage sensing board. So power supply logic section kind of has two main parts here. This is a quad comparator, and this is where the overcurrent sensing and trip out works in the inverter. So we've a programmable both positive and negative current trip. And then this guy here is a 8 input NAND gate, and whether we get a current trip or we get a fault from any of the Tesla Igbt gate drive boards, any of those trips a fault like a DSAT or an under voltage alarm, we will immediately trigger this PWM inhibit pin, which will hardware shut down the PWM generation in the microprocessor. Digital outputs, so we control the main contactor and the pre-charge relay here through just a transistor array. Nothing too exciting there. Inputs, just basic low pass filtering and scaling for things like the forward and reverse signal, the start signal, brake signal, and so on. Analog filters here then we have for the brake transducer, the accelerator pedal, and the DC bus sensing here. So again, very straightforward passive filters. Temperature sensors, again the two that we are using, we've got one of the heatsink sensors and one of the motor case sensors, again just going through pull-ups and simple low-pass filtering here. Encoder channels. The Tesla encoders already have built-in pull-ups, so we don't need to do anything there. We just use basic low-pass filtering, again just to take out high-frequency noise. And excuse me, at 36 PPR, we can be quite vigorous with these low pass filters. This guy here, DC bus discharge control, is a very simple circuit. Just a little NPN transistor which switches on and off the DC bus discharge card in the inverter, which is just designed to discharge the high voltage capacitors. So that's a basic run through of how the circuit works. Basically, looking at the PCB, then it's basically the exact same, dimensions of the Tesla card. These mounting holes around the periphery here are in the same place. We're obviously again using the same connectors, the JST CPT connectors. in the, again, reasonably close to being the same locations as they are on the Tesla board. So this should be pretty much a drop-in and plug-in replacement. So one thing to note, well, thankfully the alarm has managed to turn itself back off. So one thing to note here is that this is a 4-layer board, and I decided to make it a 4-layer board for a few reasons. One is I'm a little bit lazy and I wanted to get it finished quickly. But the second one is I wanted a full ground plane on this PCB. And I think that's important, given, you know, that we're going to be pushing over 1,000 amps per phase into a motor here. So, you know, anything that you know, helps the microprocessor here and not get a glitch is good news to me. And of course, as you can see here, it does make it much less cluttered here just on the tracking. I mean, the tracks that you can see here, the green tracks are on the top layer and the purple are on the bottom layer. And you'll see things like this capacitor here, this C37. So you'll see there's 2 vias connected to this. So this via here connects it to ground, and this via here connects it to the 5-volt line. So basically what we have, if we highlight the power planes here, so if I want to show you the ground plane, so you'll see here that the red is the ground plane, which is layer 2. So if we zoom in here on this capacitor again, you'll see that that via connects this pad of C37 to the ground plane. And if I was to show you the 5-volt plane, you'd see that this pad here is connected to 5 volts. So that is that's kind of the PCB, guys. We will be getting some of these now ordered fairly soon. I'm going to just triple check everything here as much as I can, just to be sure that I've got a reasonable chance of getting it half right first time. So I guess one question that people are going to have is, you know, what is the kind of price penalty to pay for having a 4-layer board? Well, if we look at the size of the PCB, it's 168 by 84 basically. If we jump over to this is Seed Studio, this is where I tend to get most of my boards from. If we put the size in there, so 168 by 84. So for example, on a 2-layer board there, 10 of those would be costing me, you know, base price of about 30 euros there. So, you know, pretty cheap, like about 3 euros per board. Now, jumping that up to 4 layers then, so 168 by 84. You know, it does get you know, considerably more expensive. Like it's kind of 94 euros for 10 boards, so it's about 3 times the price basically to have a 4-layer card. Now, as you would go up on volume here, you know, that price wouldn't be as bad. So, but I think, you know, 9 to 10 euros per board is, you know, perfectly fine for me at the minute. Yeah, so that's kind of about it, guys, really. There's not a lot to say here other than, you know, just wanted to give you a run through this circuit, show you what I'm doing, and, you know, let you know that we're still making good progress here. So, all right, we will see you in the next video. And not really sure what I'm going to be doing on the Tesla stuff until I get these boards in. I am having a look at the charger, by the way, so we might well be going down a similar avenue with the charger, because that looks to have, you know, a control board type of a setup again. All right, so that's enough of me rabbiting on here. So we will see you guys in the next video. Thanks for all the support. Hope you're enjoying this. We will be releasing these design files soon. I do want to get it reasonably right before I do that, because this is a serious piece of kit that can generate a lot of power. So I don't want someone going off half-cocked with this thing and you know, blowing up their house, their cat, and everything else. So, all right, see you guys next time. Don't forget to subscribe and leave me a like, and happy tracking.